Uh, I welcome you to this brief discussion. I want us to have regarding the F test. Put in very different terms, or maybe in very simple terms rather than different terms. What we are interested in doing when we are carrying out this F test is we want to test how good our model is as an explanation. And the usual way we approach this is to say ratio of what the model explained. This is measured by ESS or the R squared. This divided by ratio of what the model failed to explain, which is measured by RSS or 1 minus R squared. Okay, so these are two approaches to saying the same thing. Let me try to find a way of having the division sign. I'll put that. So this is what we are trying to do. But what we know is that the model we used to explain the variation in earnings, where our dependent variable is earnings here, only had one explanatory variable. So if we think in terms of the degrees of freedom, and these degrees of freedom are k minus 1, where k is the number of estimated coefficients, we estimated the coefficient of the intercept term and coefficient of education. So this is an intercept, this is a slope coefficient. Now, in terms of making an explanation of the variation of earnings, the intercept does not contribute to the explanation. The explanation is being done by education. So, the degrees of freedom therefore are two estimated coefficients less the constant. We take it out, and the answer we get, okay, so that's equal to 2 minus 1, okay, and the answer I get is 1. This thing is misbehaving. I want a number there and no decimal places. So we have 1 degree of freedom for the model. This is what you see here. They are saying we estimated 2 coefficients, but one of them was the constant, so we take it out. If you think of your model in deviation form, it is actually B1, the slope coefficient, x plus the error term, plus the error term, where this y is, where your small y is equal to your big Y minus your Y bar, and your x, small x, is equal to your big X minus X bar. Okay. So if we were to square both sides, we end up having y squared is equal to beta 1 x squared plus error squared, now plus the cross product of beta 1x and the error, but by the assumptions of classical linear regression modeling, that cross product when summed is equal to 0, because we know that the covariance between x and the disturbance term is 0. So we are actually left with these things, these squares. Now if we sum them, if we sum the left hand side and we sum all terms to the right hand side, then what you get is, to the left it will be total sum of squares. Notice I'm saying sum, which means we have done the summing, and to the right it will be equal to ESS plus where that's the problem of working in Excel, because now it wants to read everything as a formula, where now this term here, b1x squared, is your explained sum of squares. This is what the model is offering in terms of explaining the variations we observe in our earnings. And error squared is your residual sum of squares. Okay, so this is what the model failed to explain, what the model explained, the totality of what should have been explained. Now if you divide everything by TSS, just to help you see something important here, ESS and you have TSS, RSS, and you have TSS. If we do this, you will notice that this over that is 1. Okay, so we end up having a 1 here is equal to, and your ESS over TSS is your R squared. I hope you remember this. Your ESS over TSS is your R squared. Now what we call ESS is the regression sum of squares. This R here is your explained, that is what the regression explained, and the SS there means sum of squares. So the ratio of this number here over this number here gives us that number there. Okay, now and what the model fails to explain is the residual sum of squares here over the total sum of squares, which can easily be written. So now let's write this. This is our R squared, and this is plus RSS over TSS. Okay, so if I want to know what RSS over TSS is, RSS over TSS equal to, from this particular relationship I have here, I have to take R squared to the other side so that I remain with this only. So that's 1 minus R squared. This is what I have here. So what the model failed to explain is 1 minus R squared. What it explained is R squared. Okay? Or it's also called ESS, or it's called the RSS. Now, once you have understood this, then the test itself is much easier to carry out. The null hypothesis claims that the slope coefficient is equal to 0. The alternative claims that the slope coefficient is not equal to 0. Then we have, of course, to find the critical values, which I have indicated as F crit there. Your F crit has got numerator degrees of freedom. This numerator has some degrees of freedom here, which are k minus 1. And the denominator there has degrees of freedom. It is the sample size minus the number of coefficients we estimated, which is k. So in this case, it will be equal to, I'm using a sample of 200 here, less 2, and that will be 198. Okay, you can see the 198 there. Okay, so now what is happening here is our F observation, our F distribution has the following parameters that are very important for finding the critical value that we will use to execute the test. So it has numerator degrees of freedom, which are k minus 1. That one we have there. This numerator is associated with the degrees of freedom. And denominator degrees of freedom, the denominator here, which is what we failed to explain, is n minus k degrees of freedom. And then the level of test here, let's say we're carrying it at some level alpha percent. And so we have our alpha here, then we close. Now this, of course, entering the values we have done, we see the numerator degrees of freedom is 1. The denominator degrees of freedom is 198. And let's say we're doing this at 5%, so our alpha is 0.05. You close. This should give you some answer from the table. Now your F table is like this. Let me just explain it a little bit. It's a very, very long table. You should be able to interpret it. Now, I recall someone asked me in class, why do we say it only has one critical region? And I did mention that we didn't want to now bring complications into the lecture. But the simplest answer I can give you is that if you look at this test here, it is a right-hand test. It is not centered around 0. So there are no negatives here. So it can't have another tail. Remember that the essence of us having two tails in the T and the normal distribution is because the test here, the distributions are centered around 0. And so to the right you have positive values, to the left of the line of symmetry, which is 0, you have negative values. So here this is not a symmetrical distribution. So it starts from 0 onwards. It's a right-hand test. It only has positive critical values, if we can say it that way. So now what you will see is that it has the numerator degrees of freedom, which from what we were doing relates to what the model managed to explain, and it has denominator degrees of freedom, which you read in this direction. These relate to what the model failed to explain. Then the PR here is the p-value. So these p-values are reported for up to about 1%. There's something missing in the first row there. So this is 25%, this is 10%, this is 5%, this is 1%. Now we are carrying our test at 5% level of significance here. And we have 1 numerator degree of freedom and 198 denominator degrees of freedom. So we are under this column where we have 1 numerator degrees of freedom. We want to look for 98 here. So these numbers, we'll find them here. Sometimes they are labeled there. You keep scrolling until you get there. Right? Now you see they are this side. because it's a continuous table. Now they are this side, now they are that side, now they are this side. Now we reach, I think this is the end of the table. We actually don't see 198, but 198 is for all practical purposes equal to 200. So we are here, and we want, this is the PR column, and this is the column for one numerator degree of freedom. So we want this number here. That's what we are looking for. We are looking for 3.89. So we come here, 3.89. That's the critical value. Okay. In terms of this, it is about 3.89. That's the critical value. You see that. Then the next thing is to state our decision rule. The decision rule is if our F observed is greater than our F critical, reject your H0. Remember, your H0 said the slope coefficient is 0. That is, it is claiming that education does not explain anything at all. If this doesn't hold, then you should fail to reject. That is what we have stated here. If we find the opposite, that is where your F-obs is smaller than the critical value, then we should fail to reject the null. So now we calculate our F-obs, which is equal to, now using the information we have here, you can use the ESS, which is that, and the RSS, which is that, or you can use the R squared, which is that, and 1 minus R squared there, and adjust with these numbers. You get the same answer. So this is equal to, let's try to do it now. This is equal to your R squared. Maybe let me just write the formula. Someone might be confused here. Your R squared divided by K minus 1, right? Close that, over 1 minus R squared divided by N minus K, and I close. Okay, so the corner bracket over the division sign is what we are saying numerator degrees of freedom. And numerator, this is the explained sum of squares, or what the model managed to explain, and then we adjust that for its degrees of freedom, and what it failed to explain, adjusted for its degrees of freedom. Now once you have done that, you can now say this is equal to my R squared, which is that, divided by my degrees of freedom, which is that, over my 1 minus R squared, which is that, over my N minus K, which is that. I close this, close that, say okay. Okay, I get this number here is my F observed. You see, this is the F observed you have calculated by Excel. Okay, so using the R squared approach, I got the same F observed as that. Now the next thing, or maybe before I do the next thing, let me show you an alternative method. Or an alternative method is to say this is equal to your ESS over K minus 1, everything over your RSS over N minus K. You see, what the model explained adjusted for degrees of freedom over what the model failed to explain adjusted for degrees of freedom. Now, if iterate this thing as a formula, okay, so that's the alternative formula, equal to what the model managed to explain, which is the ESS, is this number here, and we are dividing that by the numerator degrees of freedom, and that over what the model failed to explain, the RSS, which is that, divided by the denominator degrees of freedom, which is that. You close, say okay. You see that you get the same F. Okay, so these are alternative approaches. This is called the sum of squares approach. This is called the R squared approach, and you can have an alternative one in the context of a bivariate regression, that is a regression with the dependent and only one explanatory variable. There is a relationship between the T statistic you get here and the F. Okay, so your F observed here is equal to your T squared, and this means if I come here and I say equal to my T is that, I square it, there you go, I get the same answer. Okay, so let me reduce the number of decimal places. Why did something move like that? Right, so this is the T, let me call it the shortcut. It only works when you have a bivariate regression. So now imagine you are in the exam, I give you a regression where the F is not reported, but I have given you the regression and I have given you the T values, and I ask you, is the model significant overall? That is, I want you to test the overall significance of the model in a bivariate context. You know that your F statistic is your T squared. If you square this number, you get the F. Then this is your F observed. You would have obtained your F critical from the tables. Now our decision here said if our F observed is greater than our F critical, we must reject H naught. So our F critical is 3.89. And here we got our F observed far to the right, which is 34.05. It's a very big number relative to the critical value. So we are deep into the shaded region. So therefore our conclusion is, since F orbs is greater than F crit, reject H naught at the 5% level of significance, and conclude that the model is significant. Okay, that is, the model is a good explanation. Essentially, that would be the process of carrying out your F test. What is important is to understand the relationships. Depending on what you are given in the question, you should know which formula to use. Do I use the R squared approach? Do I use the ESS approach? Do I use a T approach? In each case, you arrive at the same answer. Of course, this T shortcut is only used in a bivariate regression context. I will stop here. I hope this is helpful to you.